To take full advantage of a 35mm adapter, it is important to understand the three key factors that affect depth of field. These factors are lens aperture size, focal length of the lens, and camera to subject distance. Aperture size is the most common and practical way to alter the depth of field. The aperture of a lens is the adjustable hole or opening through which light passes. The size of the aperture is adjusted by changing the f-stop number on the lens. To understand how lens aperture affects depth of field, it is necessary to understand a concept called circle of confusion. When a light hits a given point of an object, rays are bounced off that point in multiple directions. The rays that reach the lens form a cone shape. The light rays are then bent by the lens to converge at a single point. When this point falls on the focusing plane, then that specific point of the object is in true focus. Depending on the camera and format being used, the focusing plane could be a CCD, which is the light recording element in a DV camera, or it could be actual film. As we will see, in the case of the 35mm adapter, the focusing element, or ground glass, acts as the focusing plane. Since our entire scene cannot be in true focus, some light rays will converge in front of or behind the focusing plane. In these cases, the cone shape of light rays will form a circle on the focusing plane. This circle is called the circle of confusion. Luckily, a circle of confusion can only be detected when it reaches a specific size. This set size is called the permissible circle of confusion. When a given circle of confusion goes beyond the size of the permissible circle of confusion, then we see this as an out-of-focus area within our image. In reality, the permissible circle of confusion is microscopic in size, but for illustrative purposes, let's say that this red dot is our permissible circle of confusion. Any circle of confusion that is larger than this red dot will appear as being out of focus, and anything smaller than this red dot will appear as in focus. Let's say that the lens is focused on the subject and that the plane of true focus is here. Light rays will bounce off this point of our subject and into the lens. The lens bends the light rays, and in this case, they converge on the focusing plane. If we compare the diameter of the permissible circle of confusion to the diameter of the cone shape, we see that they match at these points. The region between these two locations is called the depth of focus. The size of the depth of focus determines the size of the depth of field. They maintain a constant size relationship. When one grows larger, so does the other, and vice versa. So what happens to the light rays of an object when it is not within the depth of field? A single point from this object, which is outside of the depth of field, bounces light rays into the lens. The lens bends the light rays and they converge here outside of the depth of focus. So this object would be out of focus in our image. We can also see that this point on our object will be out of focus because the circle of confusion on the focusing plane is larger than our red dot. The further outside of the depth of focus light rays converge, the larger the circle of confusion will be, and the more out of focus that part of our image will be. Keep in mind that all of this is occurring for every point that is bouncing light rays into the lens. It is the countless number of points and circles created on the focusing plane that make up our actual image. Also keep in mind that the cone of light rays, after passing through the lens, is inverted. So light originating from this point, at the top of our subject, will be translated to the bottom of the focusing plane. And light originating from this point, at the bottom of our subject, will be translated to the top of our image plane. The same holds true for right and left as well. This creates an inverted version of our subject matter, and is one of the major issues with using a 35mm adapter. There are ways to accommodate this issue, which we will discuss later. So how does all of this relate to how aperture size affects the depth of field? When the diameter of the aperture is larger, the light rays make a more drastic change of direction to converge. So moving our red dot to align with an area of the cone that has the same diameter, we see that our depth of focus has become much shorter. Since depth of focus and depth of field are directly related to each other, this means that the depth of field will also be short. When the aperture is small, the light rays make a much slighter change of direction to converge. This increases our depth of focus and depth of field. In this case, there is much more room for the light rays to converge within the depth of focus, so much more of the image will be in focus. The size of a lens aperture is determined by what f-stop number the lens is set at. F-stop is not a physical part of a lens. It is simply a number that corresponds to the current size of the aperture. To find the diameter of the aperture, we simply take the focal length of the lens and divide it by the f-stop number. This formula is important because it tells us that f-stop and aperture are inversely related. A larger f-stop, such as f16, creates a smaller aperture opening inside the lens. A smaller f-stop, such as f2.8, creates a larger aperture opening. So the keys to keep in mind with aperture and depth of field are as follows. A low f-stop setting creates a larger diameter aperture and a short depth of field. A high f-stop setting creates a smaller diameter aperture and a long depth of field.